In 29C, we look at z-scores, and what we're doing is we're standardizing the normal distribution. What a z-score tells us is how far from the mean a specific data value is, and what it really means is it tells us how many standard deviations away we are from the mean. To calculate this z-score, this standard score, we have two ways of doing it. The first of which involves these tables that are found in your text as well as in your formula pack. And what they're finding is the area to the left of the A value. So in both of these, it's to the left of each z-score. And one is for negative z-scores, scores that are below the mean, and one is for positive z-scores, scores that are above the mean. But you have to remember that this is going from the z-score all the way to the left. So we'll look at using these in just a moment. The other way we have to deal with these is, well, we could use calculus, and take this integral, but it's not real pretty. But the calculator can do this for us too using the normal CDF. So if we're looking for z less than a, we use normal CDF negative 1 times 10 to the 99th, comma a. If it's greater than a, normal CDF from a to b, oh, these are switched around, I'm sorry. Greater than a would be here, and if it's between two z-scores, a to b. Using the table, we have to do a little bit of subtracting and piecing together these areas. The calculator can do it real quick for us, but you're going to have to do things without your calculator. So we're going to look at this both ways, both with the table and with the calculator. I score 73%, where the mean was 68% and the standard deviation was 10.2. So I'm going to change this to a z-score. So here's the mean, 68. I'm at 73. To find the z-score, we're going to do 73 minus 68, our score minus the mean, divided by the standard deviation. And that is equal to 0.49. That means I'm almost half a standard deviation away from the mean there. In the second situation, in HL, I score a 66%, but the mean was 62. Lower scores than in SL. Let's see how we compare to the mean. 66 minus 62 divided by the standard deviation of 6.8, that's equal to 0.59. So relatively speaking, we did better in HL. We're farther away from the mean in terms of what's considered normal. That's what a z-score can tell us. It's a standardized score. So now we're going to find some probabilities. And I find it very helpful to draw these pictures. Put the mean in the middle. The standard deviation is 7. And we want to be less than or equal to 69. So we're finding that entire area, that probability. And what I'm going to do is change 69 into a z-score. And this z-score is equal to 1. And if I go to my table, I want 1.0 as my z-score, so here's 1. And I'm above the mean, so I'm using this page. 1.00, that's going to be in this column. Right there is my probability. That's from, if we look at the diagram, it's from a z-score all the way to the left. So again, our answer would be 0.8413. And just to show you what we can do on the calculator, we find these commands again in the distribution menu, second, and then variables. We want choice 2, and we're going from negative infinity, so negative 1 times 10 to the 99th, comma, our value, which was 69, comma, and then we put the mean, and then the standard deviation. And we get the same probability, 0.8413. And we could have done it, if we would have used our z-score, we could have done it much quicker just by saying normal CDF, and my z-score was 1, so I'm going from negative 1 times 10 to the 99th, comma 1. If we leave off the mean and standard deviation, we're saying that these are standardized scores, these are z-scores. And notice we get the same thing. So there's 3 different ways of getting our correct answer. For the second one, if I draw my picture, the mean is 62, 58.5 is down here, and 71.8 is above the mean, and we want the area in between here. I'm going to change these both into z-scores. The z-score for 71.8 is 1.4. The z-score for 58.5 is negative 0.5. So if I go to my table, I'm going to look up negative 0.5, negative 0.50. So there's negative 0.5, there's my 0, 0. So that means that the probability from negative infinity to that first z-score is 0.3085. And that probability is this area in this tail. When I look up 1.4, I'm finding the area from right here all the way back that way. So what I'm going to have to do to find this shaded pink area is I'm going to have to take this new area that I'm about to look up and subtract off 0.3085. So I'm going to go to my table and find 1.4. There's 1.4, it's 1.40. So I use this first column again, 0.9192. So my area for the pink area, I'm going to take 0.9192. That's from 71.8 all the way to the left. And I want to subtract off this tail that I don't want. And the probability that I get for being between 58.5 and 71.8 is 0.611. So find k for which x is less than k, given that x is normally distributed with a mean of 70 and a variance of 100, which means that our standard deviation is 10. So what that tells me is that my mean of 70 is right here, and if x is less than k, the probability is 95%. That means that, well, to the mean, the area is 50%. That means in here has to be 45%. And what I need to find is I need to figure out what z-score gives me that. And so what I'm going to do is I'm going to come back to my table, and I'm going to find what area gives me that 95%. And I'm going to find the area that's closest in the body of this table. So I'm looking for 95%. Here's 95. 2. And when we look for the closest probability to 0.95, we see 0.9495 and 9505. Those are both equidistant away from the probability that I want. So I can take a z-score that's directly in the middle of these two. And 0.9495 comes from 1.64, 0.9505 comes from 1.65. So the z-score that I'm going to use is 1.645. That's halfway in between these two. The only time you can really infer this is if it's directly halfway in between two things that we have. So in this one, my z-score, 1.645, that has to equal our k minus the mean divided by our standard deviation. And we can solve this for k, finding that k is 86.5 millimeters. And another way to do that in our calculator is to use the inverse normal command in that distribution menu, and you put in the probability, the mean, and the standard deviation, and it will spit back your data value for those numbers. Here are some problems to go along with this section. Now we're going to move into 29D. D just takes this idea of normal distributions, and we look at application problems. Suggestion for this is sketch the bell curve, label the mean, put the standard deviation down on paper, label the data values you're given, shade the desired area, and then find it. Find what you're looking for. But it's very helpful to deal with pictures here. So here we have rugby players, normally distributed for their heights. Mean is this, standard deviation is 7. Find these probabilities. So I'm going to draw myself a picture, 179, and I want to be at least 175. So that means all of this is what I'm looking for. And what I want to do is I want to find a z-score for 175. And doing that, we would take 175 minus 179 and divide by 7. And once we have the z-score, we can go to the table, and the table will tell us what the area of this tail is. And when we look that up, we find the area is 0.384. And the reason we have to look that up is because the table only tells us what's less than any z-scores. So to find my probability, I'm going to do 1 minus 0.384. And that gives me a probability of 0.716. Or if we're allowed a calculator, we could use the normal CDF with 175 to infinity, with a mean of 179 and a standard deviation of 7. For B, label the mean, put my data values on, and I'm going to change them to z-scores. So you should do that and look up the z-scores, and we're going to get two probabilities. When we look up the first z-score, it's going to give us that tail. When we look up the second z-score, it's going to give us from 190 all the way to the end. To find what we want, to find the area in between these, we're going to have to take the big area minus the small area, and what you should end up with is 0.843. Or in the calculator, we can just punch in our data values with the mean and standard deviation. And that will give us 0.843 also. So we have 80% should pass. We're expected to have this mean and this standard deviation in a normal distribution. What that means is we want to know what score is right here so that this whole area is 0.8, which means our tail over here is going to be 0.2. And that's the probability I can look up in our table. And then once we have that z-score, we can set that equal to k minus 62 over 13. Or similarly, we can take the inverse norm of 0.2, because the probability less than this value is 0.2, 62, 13, and that will also get us the correct value, the correct score for k. In the last example here, it says to find the mean and standard deviation given these two probabilities. So here's the mean, here's 50, x bigger than 50 is 0.2. X less than 20 is 0.3. And what we end up with is a system of equations. 20 minus the mean divided by the standard deviation. If we look up .3 in our table, or we use inverse norm 0.3, what we get is a z-score of negative 0.5244. That's the closest z-score that we can get, and we'd probably lose a decimal place if we use the table, but using inverse norm of 0.3, that gives us this value. And then we can also do a similar idea with 50. And the z-score we're going to do, what we're going to look up is 0.8. So we're looking at 0.8 or using inverse norm. 0.8, again, we have to look at what's the probability less than the 50. And we get a system of equations. Negative 0.5244 times the standard deviation plus the mean equals 20. 0.8416 times the standard deviation plus the mean equals 50. And we can solve this system using whatever methods we want, matrices, elimination, whatever, and we will end up with the standard deviation being the standard deviation is 22, and the mean ends up being 31.5. And here are a few application problems for you to work on as well.